This video is for Wednesday, July 27th, Math 0324. We just have one item on the agenda today. That's working homework number 12, which is the rules of exponents. So homework 12, rules of exponents. This one's got 23 questions. Before I even open any of the questions up, rules of exponents, there are three really important ones, and then there's a handful of others. Rules of exponents. Most of the rules of exponents are easy to do, but they're similar rules, so people get them mixed up a lot. Do the wrong one at the wrong time. So anything to the 0 power is 1. Anything to the first power is itself. If you are multiplying powers like x to the m times x to the n, one key thing is that both of those bases are the same. They're both an x. And then in the answer, that part doesn't change. This is another case where that's kind of like a common denominator. Those have to be the same and they don't change, just like when you're adding a common denominator. And then the weird part is when you're multiplying powers, you add the exponents, you don't multiply them. And that's a confusing point sometimes. If you're dividing powers, x to the m divided by x to the n, if you get rule 3 right, then rule 4 makes sense. Then you do x to the m minus n. And then there's 2 left. If you do x to the m, and then that's raised to its own exponent like n. This is one base with a double exponent. That's when you multiply the exponents. So there is a time to multiply exponents, but there's a time to add them. And maybe a good way to remember it is you never do them like they look. So if it looks like you're multiplying, don't multiply them. If it looks like you're doing to a power, you don't do it to a power. There's another rule instead. And finally, there's even negative exponents. X to the negative m is just 1 over x to the positive m. Negative exponents have nothing to do with negative numbers. In fact, they often don't even have a negative answer in them. All they do is they make the base of the power, the x, move to the other half of the fraction, and then the exponent changes from negative to positive. So we're going to definitely be using all 6 of these throughout this homework. That's why I wanted to make the list before we even, I don't need to do this, go back. Okay. Okay, so homework, this is homework number 12, rules of exponents. There's 23 questions here. I guess during that big shutdown of my math lab when they were closed, where it was down all weekend long, I guess this is one of the improvements they were working on. They have this over here on the side so you can jump to a question now. It used to have to click this little 3-line thing to make that visible. So I guess they think this is an improvement, but to me it kind of gets in the way, so I'm just going to move that out of the way. Okay, so write the expression without using negative exponents. It's kind of an unwritten rule that you should never in a final answer put a negative exponent in the final answer. But that was one of the 6 rules I just mentioned. 9 to the negative 1, it's literally 1 over 9 to the positive 1. That's all the negative exponent rule does. Let me see where I'm at, right? Oh, I'm here, okay. So 9 to the negative 1, the rule says you do 1 over 9, and then by doing that, the exponent changes from negative to positive. And because 9 to the first power is itself, that's another rule, then I don't need to write the 1, the exponent 1. You do need the 1 in the top of the fraction though. So that's the answer, 1 over 9, and notice there's no negative in the answer. So that's a confusing part for students, as they think it has to have a negative in it. 2 of the choices had a negative too. A lot of people pick those. but it's d 1 over 9. And then also, this is a good point right here. Let me do this over here. There's a difference between 2x in parentheses, 2x to the negative 2, versus 2x to the negative 2 without parentheses. If there are no parentheses in an exponent, then it only applies to the thing it's next to. This negative 3 only applies to the x. It doesn't apply to the 2 because there's no parentheses there. So it helps sometimes with negative exponents. Draw the fraction line. Currently there is no fraction. That means it's literally over 1 right now. So if the bottom of a fraction is blank, you don't have to put the 1. If the top of a fraction is blank, you have to put a 1. The 2 is in the top of the fraction. It does not have a negative exponent, so it stays in the top of the fraction. The x is in the top, but it has a negative exponent, so I move it to the bottom, and that's what makes the negative exponent turn into a positive. This would be the answer, 2 over x to the third, if there were no parentheses. When there's parentheses, then it applies to everything. So the entire 2x drops to the denominator. The negative 2 changes to a positive 2. And then there's literally nothing left in the top, but the top of a fraction can't be blank, so we have to put a 1. And then you could square both of these because it's multiplication and not addition. So they may or may not do this step, but another possible answer would be 1 over 4. 2 squared is 4, and x squared is just x squared. So they might have this as the answer. Or they just left it like that just to show what's happening. So it's 1 over, and the 2 gets squared. You could write a 4 for that, and then x squared. It would be more simple if they put a 4 for that, but I think they want to show exactly what's actually happening to that thing. And that's a good point too. Let me go back to that. Sometimes a student will get a multiple choice question in essence right. They might have this on their scratch work, and they're looking at the test and that choice isn't there. So they think they did something wrong. But sometimes it's just that the answer to the test is equivalent to the one you have, and if you don't realize that, you can miss a multiple choice question because of that. If you didn't realize 2 squared is the same thing as 4, then you might not have known the answer was C. That's a common thing that happens. So here's the one I did. I made up an example similar to this. This one does not have parentheses, so only the x goes to the bottom. The x is going to go to the bottom and become x to the positive 4. But the 9 doesn't go down there because it does not have a negative exponent. If there was a parenthesis around it, then they would both go to the bottom. So this is a 9 over x to the 4th. Little details like that make a difference. And then if the number is negative, that's okay. Again, negative exponents don't have anything to do with negative numbers. Negative a to the negative 5, but there's no parenthesis. So put this over 1 for a second and then redraw your fraction line. So the negative would stay in the top because it's not in parentheses. The a would drop to the bottom and become positive 5. Once there's something down here, then this 1 goes away because I didn't even really need to draw that 1, but I was just showing you where the bottom of the fraction was. But whether I put 1a to the 5th or just a to the 5th, that's the same thing. And then, in essence, the top is blank, so I need to put a 1 there. The top can never be blank. So negative 1 over a to the 5th. So if the original problem is negative, it basically just stays negative. Negative exponents have nothing to do with negative numbers. So if the original is positive, it stays positive. If the original is negative, it stays negative. The negative exponent doesn't affect the negative number. So it should be negative 1 over a to the positive 5 power. And then we've met the rule that you don't leave negative exponents in your, write the expression only in positive exponents. You never want to have a negative exponent in your final answer. You can have negative numbers, but not negative exponents. Now, the opposite is true too. The negative exponent might be in the bottom. That's okay. It doesn't matter where it is. You just move it to the other half of the fraction. Do that again? Yeah, I'm so used to doing that. So 1 over 2 to the negative 3. I currently have a 2 to the negative 3 in the bottom. If I move it to the top, then it becomes positive 3. And if there's already a 1 there, that doesn't matter anymore because 1 times anything is the anything. The bottom's blank. I can put a 1, but we normally don't in the final answer. So 2 to the third over 1, or just 2 to the third, or maybe they're going to put 8. 2 times 2 times 2 is 8, so it could be either one of these. That's where, if it's multiple choice, we have to check. And they might have a 1 we don't have if we don't know that. Type an integer or a simplified fraction. So it doesn't say type exponent, so I'm thinking they want the 8, not the 2 to the third. Okay, so there was something else I wanted to mention. Oh, yeah. So watch out for this. Once people learn these rules, they want to do it to things that they don't apply to. So if you get negative 3 x to the 4th, it's not x to the 4th over 3. You don't put this negative 3 in the bottom. That's not an exponent. The rule's about exponents, not about negative numbers. So just because a number is negative, you don't move it to the other half of the fraction, only if an exponent is negative. I've seen people do this before, and it's kind of like you teach them something new and they just want to do it to everything that looks like it, not the stuff that it actually applies to. Okay, so now we move to the next rule, z squared times z to the 6th times z to the 7th, or even if you just had 2 of these. Let me just do the first 2. Z squared times z to the 6th. This is a rule of exponents. This is rule number 3. I have 2 powers multiplied together. They both have the same base, so the base doesn't change. And I just take their exponents and add them. Z to the 2nd times z to the 6th is z to the 8th, because you do 2 plus 6. The work here is usually pretty easy. Anybody could do 2 plus 6. So the good thing is you don't have a lot of heavy math going on here. But the rules are easy to mess up. If this is multiple choice, they're going to put a z to the 12th because somebody thinks it's 2 times 6. It looks like 2 times 6, but it's not. The reason it's not is z squared literally means z times z. That means you have 2 of them. Z to the 6 is z times z times z 6 different times. And then these get multiplied together. So I literally have 1, 2, 3, 4, 5, 6, 7, 8 of them. When there's 2 z's and another 6 z's, I get a total of 8 z's. So that's why the rule is adding and not multiplying. Easy to do, but also easy to mess it up. And then once I've done that, then I just do it again. Normally you just do this twice, but you can do it 3 times. So this part's z to the 8th, and then I do another time z to the 7th. That's z to the 8 plus 7 is 15. Okay, regular numbers have nothing to do with exponents. So the regular numbers, you still do them like you did back in middle school or even elementary school. So I've got a negative 10, x to the 5th, y to the 3rd, times 7x to the 6th, y to the 5th. There's no addition or subtraction here, so you can just do each part together. I can do negative 10 times 7, just like back in middle school. Negative 10 times 7 in middle school is negative 70. It's still negative 70 in college, because those are just regular numbers. What's new here is the exponents. So x to the 5th times x to the 6th, that's got a special rule. And that's the bases have to be the same. They are. And then you don't multiply, you actually add. So that's x to the 11th. Y to the 3rd times y to the 5th is y to the 8th. Notice I can't add these together and get 19 because they have different bases. So that's as far as you can go. I don't drop the 70 to the denominator because it's not a negative exponent, it's a negative number. Negative 70, x to the 11th, y to the 8th. I don't know why I keep doing that when I don't have to. Okay, so negative 70, x to the 11th, and then y to the 8th. Okay, 3m to the 4th times negative 7m times 2m to the negative 6 to the 0. Now, this looks more complicated than it actually is. 3m to the 4th, notice there's no parentheses there on that 4. Then there is a parenthesis for negative 7m, but it doesn't have an exponent. And then another parenthesis for 2m to the negative 6 to the 0 power. There is a rule of exponents for this right here. That's when you have one base and what I call a double exponent. M to the negative 6 to the 0. I'm doing it twice. I'm doing an exponent 2 different times. That is rule number 5. X to the m to the n is x to the m times n. But because the one of the two exponents is a 0, then rule number 1 applies, which is the easiest rule of them all. Anything to the 0 power is 1. And if it's a parenthesis around it, then the whole thing is 1. This whole thing is in parentheses, has this 0 power. This applies to the whole thing. This whole thing equals 1. You could do other work to it and work it out slower, but it's easier if you just recognize something to the 0 power is 1. Then I lose all this complicated part. And anything times 1 is itself, so that's not going to matter anymore. So I have a 3 times a negative 7, that's negative 21. Now we're kind of doing like this problem where I did negative 10 times 7 is negative 70. 3 times negative 7 is negative 21. M to the 4th times m, and this is tricky, m to the 5th, not 4th. A blank exponent is not a 0, it's a 1. Because if it was a 0, it would just equal 1 altogether. So x to the 0 is 1, you lose the x when that happens. X to the 1st is x. That's where the 1 is just left blank in essence. So if you don't want to get tricked by those, put a 1 on any blank exponent. And then it's actually 4 plus 1, 5. And then this times 1 is itself. Anything times 1 is itself. So the answer is negative 21 m to the 5th. If this had not been a 0 power, then I would have had a bunch of stuff in here to work out too, which would have really made it complicated. But I think they did that on purpose just to try to scare you a little bit. Like, whoa, look at all this stuff here I got to do. But nope, it all goes away because of the 0 power. Negative 21 m to the 5th. Whoops, I don't need to do that. Negative 21 m to the 5th. Okay, now we're going to be doing the dividing rule. 3ps in parentheses but no exponent, s to the 6th, 24 p to the third s to the ninth. And when it's over, that really means divided by 2. 3ps. If there was an exponent right here, then it would go to all three of these things. But it's blank, it's just a 1, so then it doesn't really matter. And then there's an s to the 6th. The bottom is 24 p to the third s to the 9th. So in the top of the fraction, there's a 3, nothing else like it. There's a p, nothing else like it. And there's an, like the end of the last problem, there's an s to the 1 and an s to the 6th. This right here is a rule of exponents. That's when you get s to the 1 plus 6. That's rule number 3. Then I'm just going to rewrite the bottom. This right here is a rule of exponents. S to the 7th divided by s to the 9th. That's when you divide powers with the same base, then you subtract their exponents. So what you're really getting is s, base never changes, 7 minus 9, which is -2. This p is blank, so it's a 1, and this is a 3. So that's a rule of exponents right there. That's p to the 1 minus 3, or p to the -2. Now, it's just a coincidence both of these equal -2. 3 and 24 both divide by 3. 3 divided by 3 is 1. 24 divided by 3 is 8, so it's 1/8. And then we can't leave these -2's in the answer for exponents, so we need to put them in the bottom. They're currently in the top. So you got your 1/8. P to the -2 can drop to the bottom and become p to the +2. S to the -2 drops to the bottom, becomes s to the +2. There's nothing left in the top, so we have to have the 1 there. Another way of thinking about this that I like to do better than doing all this is I say to myself, there's 7 s's in the top, there's 9 in the bottom. If you literally wrote s times itself 7 times, and then in the bottom you wrote 9 s's, the 7 s's in the top would cancel 7 of the 9 in the bottom. So there would be 2 s's left in the bottom. See, 2 s's in the bottom. So the easier way, rather than doing 7 minus 9 is -2, and then, oh wait, I got to put that in the bottom. An easier way in these division problems is just do the bigger one minus the smaller one. 9 minus 7 is 2. And then the bigger one's in the bottom, so the s to the 2 goes in the bottom. That's the way I like to do them. So don't do 1 minus 3, do it backwards. 3 minus 1 is 2. And then there's 2 p's where the bigger one is, so 2 p's in the bottom. 3 is bigger than 1, that's where the answer goes. Then you don't have to deal with negatives if you do that. So click the fraction button, and then 1/8 p squared and s squared. Okay, here's one with a parenthesis. So a parenthesis means the exponent gets applied to everything inside the parenthesis. 2 divided by 3 to the -4th power. But it would be different if it was 2 to the -4th over 3 without parentheses. Then it would only apply to the 2, not to the whole fraction. If a fraction has a negative exponent, the trick is you do the reciprocal. If you flip the entire fraction, then the -4 can become a +4. So in essence, they're both negative exponents. So the 2 goes to the bottom and becomes a positive exponent. The 3 goes to the top and becomes a positive exponent. And then I can do 3 to the 4th and 2 to the 4th if they want exact answers. 3 to the 4th is 3 times 3 times 3 times 3, 81. 2 to the 4th is 2 times 2 times 2 times 2, 16. (81/16). Simplify your answer, type of fraction or a mixed number, but they'll take a improper fraction, so why not leave it that way? Why waste time changing it to a mixed number? But you could if you wanted to. Watch out here because it's 6 to the negative 1 plus, not times, but plus. 7 to the negative 1. So there's 2 issues. First of all, the bases aren't even the same. And there is no rule about adding powers. There is no x to the something plus anywhere in this list here. So 6 to the negative 1 plus 7 to the negative 1. I'm just going to use the negative exponent rule. 6 to the negative 1 is 1 over 6 to the positive 1. And then you don't need to write the positive 1 exponent. 7 to the negative 1 is 1 over 7 to the positive 1. And then we got to go back to last week and add fractions that have different denominators. So 6 and 7, they don't have anything in common. So the common denominator is going to be both of these multiplied together. 6 times 7 is 42. And then you can get each one by multiplying by the other one. The 6 needs to be multiplied by the 7 to its top and bottom. The 7 needs to be multiplied by the 6 to the top and bottom. That way you're multiplying by 1 and not changing it, but that way both denominators will be 42. 1 times 7 is 7. 1 times 6 is 6. 7 plus 6 is 13. 13 is prime, so it won't divide into 42. So the only rule of exponents here actually was the negative exponent rule. 13 over 42, type a fraction. Okay, this is good. Now watch out because sometimes they either here they both have a negative exponent, but sometimes they don't both have that. So only the ones with negative exponents are going to move. 2 to the, this is number 12, 2 to the negative 5 over 2 to the negative 3. It's very good in most cases to get rid of the negative exponent right away or as soon as possible. So I can get rid of the negative 5 exponent. If I move this 2 down to the bottom, then the negative 5 would change to positive 5. And this 2 can go up to the top if I change negative 3 to positive 3. And then you can either say, okay, this is 2 to the 3 minus 5, using the rule of exponents literally. Notice you don't divide 2 by 2 and get 1. Some people do that mistakenly. Remember what I said about all these rules? You never do anything to the bases. The bases have to be the same, but then they don't change. X to the m times x to the n is x to the m plus n. X to the m divided by x to the n is x, not 1. You don't divide the bases. You actually just subtract the exponents. When they're variables, people normally don't do them accidentally. Find one here. This, like s to the 7th and s to the 9th, most people don't divide the s's. But if you give students this on a test, there's a lot of people that think 2 divided by 2 is 1 right here. And then I would do this the other way and say, okay, 5 minus 3 is going to be 2. Whether I do 3 minus 5 or 5 minus 3, it's all about 2. And since the bigger one's in the bottom, if I do a 2 squared in the bottom, then I don't have to go through the negative exponent rule. And if there's nothing left in the top, you have to put a 1. 2 squared is 4, so it would normally be more preferred to write it this way. But we did see one earlier today where they just left it 2 squared instead of changing it to a 4. But I'm guessing they want 1/4 here. Whoops. Okay, 2a to the -3, and then there's a 4th power on the outside, a to the 3rd, and then a -1 to the outside. (2a to the -3), and then the outside exponent's +4, a to the 3rd to the -1. Well, this bigger parenthesis, there's 2 things inside, 2 bases inside, so this 4 would go to both of them. And then you would, since this doesn't have an exponent, you would just get 2 to the 4th. But the a would be a rule of exponents. There's a rule of exponents for this. When you have a double exponent, that's when you multiply them. -3 times 4 is -12. And here's another one where you multiply them, a to the -3. And then 2 to the 4th we saw earlier was 16. You could move both of these to the bottom and that would change them into positives. And now another rule of exponents, a to the 12th times a to the 3rd is a to the 15th. And this is not the only way to do the problem. I could have added these negatives first, and it would have been -15, and then I could have moved it to the bottom. I could have done this first and put that in the bottom, and then have a fraction, a parenthesis with a fraction and a 4 on the outside. And if you do any of those other options, you get the same answer. So 16 over a to the 15th. (16 over a raised to the 15th power). Okay, so x to the -5, y to the 7th, all to the -3rd power because of the parentheses. So there's a -3 outside exponent that's going to apply to everything inside. X to the -5, y to the 7th. So you could handle this x to the -5 first if you want. I'm just going to go ahead and apply this to both parts. That's when you multiply exponents. The base stays the same. -5 times -3 is +15. 7 times -3 is -21. That's why we practiced that last week. And then the x has a positive exponent, so it's going to stay here in the top. The y's got a negative, so it needs to move to the bottom, and then it can become +21. And you can't divide these two. Those two are not the rule 4 because you got to have the same base for both of them, x and x. So x and y, the rule doesn't work then. So you're just stuck with x to the 15th over y to the 21st. Fraction x to the 15th over y to the 21st. You do need to move the y to the bottom because it had a negative exponent, and we want all non-zero. Well, that's something else actually, but positive exponents right here. Okay, 15 has p to the -2 to the 0 power over 5p to the negative 7 without a parenthesis. So you could do a rule of exponents and say, okay, this is when I multiply, but 0 times anything is 0, and then you'd have p to the 0, but anything to the 0 is 1, so whether you do it as p to the 0, or whether you just say this entire thing with a parenthesis to the 0 power equals 1. We had one of those earlier too. So with a parenthesis, everything in there just automatically equals 1. So we got our 1 in the top, we got our 5 in the bottom. The 5 does not have a negative exponent. It would have to have parentheses to be so. But the p to the negative 7, that could move up to the top and become p to the positive 7. That's all a negative exponent does. And because there's something up there, then you don't need to put the 1 anymore. You could, but it's normally not written that way. So p to the 7th over 5. P to the 7th over 5. Once you recognize the top is to the 0 power, boom, the whole top is 1 because of the parentheses. Okay, now we're getting a little more complicated. Number 16. 3a to the 3rd times a to the negative 3 to the 4th over a to the negative 2 to the negative 1. So we could do this rule here and here, the power rule. A single base and a double exponent, that's when you multiply the exponents. So I'm going to rewrite the 3a to the 3rd. This will be a to the negative 12 because you just do negative 3 times 4. And this will be a to the positive 2 because you do negative 2 times negative 1. Now I got 2 a's in the bottom. I could cancel 2 of these 3 in the top, leaving 1a. And then the 3 would stay in the top. That single a would be in the top because the bigger amount was in the top. And then the a to the negative 12 could drop to the bottom and become a to the positive 12. And then because I have 1a in the top and 12 in the bottom, if you do 12 minus 1, that's 11. The bigger one's in the bottom, so the 3 will be stuck in the top, and then a to the 11th in the bottom. Other things you could have done is you could have said, I'm going to multiply these 2 a's, which is when you add exponents. So you could get a to the negative 9 for this part right here. Then you could drop it to the bottom, it would be a to the positive 9. Times this a squared that's down here, that's a to the 11th too. So there's a different way of doing it, but you get the same answer if you do it in a different order here. 3 over a to the 11th. Whoops. Cancel that. 3 over a to the 11th. Okay, we seem to be switching gears now, but I think I know where they're going with this. In a square root, you try to see if it comes out exactly. A square root literally means, is there something times itself that equals that? Because 8 times 8 is 64, that's why the square root of 64 is just 8. But sometimes it doesn't come out exactly. If there's a negative on the outside, you just bring the negative into the answer. Is there something times itself that equals 400? That's a little harder to know, but there is. 20 times 20 is 400. So that's why the square root of 400 is 20. Or you can do square root of 400 is 20. So then the answer is negative 20 because the negative was on the outside. So if that happens, you just carry it along into the answer. if you get a square root of a fraction, just try to do each half of the fraction. Outside negative will come along into the answer. So I've got negative square root of the fraction 64 over 49. The answer is going to be negative. I can do the radical to each half if it's multiplication or division, but not addition or subtraction. The square root of 64, we did that already. That was 8, because 8 times 8 is 64. Since 7 times 7 is 49, that's 7. So the answer is negative 8 over 7. Both halves of the fraction came out exactly. Sometimes they both come out exactly, sometimes neither, sometimes one or the other, so you just do what you can. Negative 8 over 7. Which doesn't reduce because 7's prime. Okay, so yeah, this is what they're getting at. So this is symbols to know. It turns out the square root of any number or variable is equivalent to a fractional exponent. And the fractional exponent for a square root is a half. And the reason why is if an exponent is blank, it's a 1. So this is x to the 1 right here, and this in essence is x to the 1. And then the radical, when a radical's blank, it actually has a 2 here. A square root is a 2. And I think I mentioned this already, how in math we have blanks for everything. Everything has a case where there's a blank. Most blanks are 1s, but there are examples that they're not 1s, like square roots are 2s, logs are 10s. So the root goes in the denominator. So that's what I say to myself as I cover up the denominator, and it's x to the 1, and it's still x to the 1 there. And it's the denominator that causes the radical to happen. So if you get x to the 2/3 as an exponent, fractional exponents are radicals, and x squared is what it mostly looks like, so it's still x squared here. It's the denominator that goes in the root. So that would be a cube root of x squared if you were to get that one. The problem gives me 9 to the 1/2, which the first time you see this, you probably think, what does that equal? But if you know the rule that that's a square root, a 1/2 power is simply a square root. And the square root of 9 comes out exactly. So then it has a nice answer, 3. You probably would have never guessed 3 from this the first time you ever saw that. But 9 to the 1/2 is square root of 9, so the answer is 3. So it's almost like its own rule of exponents, that a fractional exponent is a radical. So we need 343 to the 1/3, and they have multiple choice for this, but they just want to say, what does it look like first? So let me write out what would actually happen. 343 to the 1/3, just like this problem, would become a radical. The top of the fraction is still the exponent. The bottom of the fraction is the root. This is a cube root of 343 to the first power. Anything to the first power is itself, so you don't need to put the 1. So the part 1 of this problem is they want you to recognize that 343 to the 1/3 is literally the same thing as cube root of 343. They want you to pick that out of the crowd. That's the cube root of 343. Maybe I didn't read it. What does it say? Which term represents the simplified form? Okay, so I see why that's not the answer. So that's what it is at first, though. But they said simplified, so is there any way to simplify this? Does this calculator have cube roots? Square root? I don't think it has cube root. Okay, so, but I do have a calculator that has a cube root feature. In this calculator, if I press the math button, there's a cube root right there. So I can go down to cube root and tell it 343, cube root of 343. And I just want to see, does it come out exactly? If it comes out exactly, we're good. If it doesn't, then we got to worry about what to do. But it does come out exactly to 7. The cube root of 343 is 7, because literally 7 times 7 times 7 is 343. So that's what a cube root means, is what number times itself 3 times makes that happen. Square root is what times itself twice makes that happen. Because 7 times 7 times 7 is 343, the cube root of 343 is 7. But it's good to know that you should change this to a cube root first. They really should have had a part A where they were doing that first, then simplify it to 7. Because otherwise this is a little misleading in that it doesn't seem like that you ever went to a radical. But that's why they made me miss this one, is I didn't read it close enough. It did say simplified, so that was my fault for not reading that. Simplified. Okay, but forget that for a second. I'm going to do it as a radical first. So what if you don't have a calculator that can do this? 256 to the 1/4 power. First, you have to know that that's the 4th root of 256. To the first power, just 256. So do you know maybe that 256 is 16 times 16? Maybe not. That's fine if you don't. But if you did, then you could have 4 times 4 and 4 times 4. And even though those keep going, a 4th root means you need 4 of the same thing on the inside to have 1 on the outside. So the 4th root of 256 equals 4. Exactly, because 4 times 4 times 4 times 4 is 256. What if you didn't know 256 was 16 times 16? Well, you can do it slower if you have to. 256 definitely divides by 2 because it's even. 256 divided by 2 is 128. That divides by 2 because it's even. 64. Now maybe you know 64 is 8 times 8. If you can keep doing 2 if you want. I could do 2 and 32 and then 2 and 16. But if you know bigger numbers, it helps you get done faster. So this is 2 times 4, and this one's 2 times 4. And the 4s are 2 times 2. So I did it in a quicker way, but the good news is you don't have to. You can do it the slow, methodical way if you have to. Every time you have 4 of the same number, you bring one of those to the outside in a 4th root. So 1, 2, 3, 4 2s right there. That brings a 2 to the outside. 1, 2, 3, 4 2s brings another 2 to the outside. When you bring more than one outside, you multiply them together. So boom, same answer, 4. So the simplified version is 4, but it's good to know that that's actually the 4th root of 256. You'd have to think of that first before you could even get to the 4. Okay, last problem is the fractional exponents. They usually put 1s in them, but they don't have to. So they have 32 to the 5/2 power for the last problem, number 23. 32 to the 5/2. Oh, I'm sorry, 36. 36 to the 5/2. 36 to the 5/2. Any fractional exponent, it's good to make it a radical. Radicals are usually easier to deal with than fractional exponents. So the 36 is inside the radical. The root is the denominator, which we normally leave blank, but I can put a 2 there. The 5 is the exponent. It turns out when these come out exactly, you can do this in either order you want. I can do the 5th power first and then take the square root, or I can do the square root first and do the 5th power second. Usually doing the root first is better because it'll make numbers smaller. In your head, you can probably tell me what the square root of 36 is. That's 6. Whoops. Then you bring the exponent down. 6 to the 5th power. 6 times 6 times 6 times 6 times 6. 7776. See, but the problem is I could have done 36 to the 5th power first. It's just that's going to be a ginormous number. 36 times 36 times 36 times 36 times 36. It's a 60 million number. But then I could do the square root of it. Same answer, 7776. So you can do the power or the root first on these fractional exponents. Doesn't matter. You can do the root first or the power first. Roots first make things smaller, so I would do that and make the number smaller. But you can go to the bigger number if you want. I did this both ways and I got 7776. Okay, so now I got 100 on that. That one was kind of long, even though each individual problem was short, or not too long. So, homework 12, all 23 problems are done now. The video today is only 50 minutes long so far, so that's because we only had to do one homework, but it was a long one. So the Monday video had homework 8 and 9, the Tuesday video has 10 and 11, and now the Wednesday video's got 12, homework 12. And once you finish them all, or you have at least 70 in each one, then you can do this quiz as much as you want. Infinite number of attempts until Friday night's deadline. So for 0324, all you got to do are these 5 homeworks and this quiz by Friday night. And then you can start concentrating on 1324 at that point. So maybe get this homework done with the videos I sent, try the quiz at least once. And if you don't get the best grade on it, then that's okay, wait, and then start working on 1324, and then come back and try the quiz a little more if you need to, if you want to get a higher grade. Okay, so that's it for this week for Math 0324. I forgot to do my magic word of the day. Okay, so I didn't even think of what word I wanted to do yet either. So you get an easy one today, since I was forgetting to do it. I'm just going to have to tell you the word, and it's not going to be spelling anything out. So we've already done COVID. We've already done monkeypox, although it was just monkey. What else bad is going on in the world right now? How about we do January 6th? So just email me January 6th, and that'll be your word of the day. I could have spelled Jan 6 over the last hour, but I forgot about it. And this is the only class where I have to do this. So you get an easy one today, January 6, Jan 6. Send that to me, and you'll be credited for watching this video. And then next Monday, I'll try to remember to spread them out over the whole hour again, so that somebody can't just jump to the end and find the magic word. So that's it for week 2, and good luck on the quiz when you take that sometime by Friday night.